Hello, everyone. This is lecture 5 of PTRE 465531, Petroleum Reservoir Geomechanics. Today, we will carry on with Module 1. We have seen the last, in last lecture, lecture 4, we saw the first example problem, which was pretty mathematically intensive, I would say, for the class level. This is not to scare anyone. I think this is one of the hardest mathematically wise problem that we are gonna see throughout the year. I think, like I promised, things are gonna get a little bit harder before they get better, easier, but they will get easier and simple. So bear with me a little bit. I uploaded an updated version of the slides a few minutes ago. There were some inconsistency in the nomenclature that actually one of the students, and thank you very much to Justin for noticing that in the latest example problems. The answers are correct. It's just the steps. I had some symbols, some minus ones that should have been T's for matrix transpose. So thank you, Justin, for that. The answers are correct and everything is okay. We're gonna get to them slowly, I believe. So the problem that we saw last time, the example problem that we saw last time is a simple one. It was, we were given a tensor and we had to find the eigenvalues and the eigenvectors. But we were not really asked for the eigenvalues and the eigenvectors. We were asked for the stress, principal stresses, in situ principal stresses and their directions. And we had to think, hey, that means I have to find the eigenvalues and the eigenvectors. And like I said, every time you see a stress matrix, which is basically the Euler's theorem that the stress field at any point can be presented by mathematically by a matrix, a tensor. Always ask yourself, is this tensor stable? Is this matrix stable or not? And it would be stable, it would make physical sense if it's diagonal and symmetric. And then we proceeded to write down the characteristic equation of the matrix, of the tensor, set it equal to 0, as we did here, and then solve for the determinant equal to 0 for to calculate the 3 possible values for lambda, 4, 2, and 1, which are respectively the greater, intermediate, and least compressive in situ principal stress values. And then for each of these lambda, we found the corresponding eigenvector. And we talked about a potentially confusing matter that many times, and especially when you are dealing with diagonally symmetric matrices, as you may have noticed in your linear algebra classes, you are dealing with a lot of situations like we had here. You have a free option. And you have a free option because like you have two equations that are basically identical. So you choose one value and that corresponds to a different value for the other unknown. You fix one unknown to get the other one. And that gives you a number of infinite options. And basically, to clarify any confusion here is that you have infinite amount of answers because a matrix, a vector pointing at one direction can have infinite number of lengths. Basically, it can be a very long matrix pointing to one direction. It can be a very short matrix pointing to the same direction. The appropriate answer, and this is how I expect to see it in your homeworks and in your exams, and I stress that, is that the matrix you will give me needs to be divided by the magnitude. So basically, you are giving me a unit vector. I want your answers always in unit vectors. I did not take points off last year, but this year there would be, because this is the appropriate way of giving a direction in a vector. It's expected that you give it in a unit vector. So, and it doesn't matter what you choose for free choice. You choose 1, you choose -1, you choose 2, whatever. Divide by the magnitude, you will find 1 divided by a square root of 2 in this case. Also, something else to say, many times people find themselves in a kind of confusing situation in exams or homeworks. And this eigenvector in inverted commas, excuse me, zero I plus 0J plus 0K looks an attractive solution, looks like an applicable solution. It fits. Like, it's the glove, remember from O.J. trial, the O.J. Simpson trial? It becomes the glove that fits. Is this a vector pointing towards a direction, though? The answer is no, it is not. So this cannot be the answer. It's not a physically correct answer. It could be a matching answer or I guess a made-up answer, something that you can pretend that it makes sense, but this is not a real matrix. This is not a real vector. It's a nothing vector. It's a null vector. So it cannot be an answer in a problem with the physical aspects that we are discussing. So don't give me this answer ever as an eigenvector. I will never ask you a question where 0, 0, 0 is the answer. I can ask you a question where 1, 0, 0 is an answer, or 0, 1, 0, or 0, 0, 1 is an answer. It would be a very nice vector, very easy to deal with it mathematically, eigenvector, but it's never an option, okay? It's a physically not correct answer. And I had a professor, it was a reservoir simulation professor. He was telling us always ask yourself if your answer makes sense before you give it. Before you write it down in the exam, before you write it down in your homework, always ask yourself if the answer makes sense. It may very well not be a physically correct answer. And we are in engineering. We are not scientists. We apply science. You need to be thinking logically if the answer makes sense. In fact, when you get to deal with more complicated problems like simulations that are long and hard and I don't know, I mean, always ask yourself, little piece of advice, I mean, friendly advice, always ask yourself if the answer makes sense before you give it. Like, or before you run this long simulation, let's say, ask yourself, what kind of answer am I expecting to see? You should never be surprised. It's like a lawyer in, how do you say lawyer? I don't know why. I brought up O.J. Simpson, and now I remember a lot of stuff from that story. But anyway, they always say, like, never ask a question if you're a lawyer that you don't know the answer. Here is a little bit, never give an answer that doesn't make sense to you. Always think if the answer that you are about to give makes sense. Anyway, enough with that. So yeah, now that we are done with, problem 1, we will proceed to rotation, general talk about rotation of a matrix along a special reference frame, to a spatial reference frame. Okay, I'm given a matrix that is in has a certain orientation in space that doesn't really depend to me. 1, 2, 3, and I want to shift it to another frame of reference, say 1 prime, 2 prime, 3 prime. 1 prime is at right angles from 2 prime and 3 prime, and so is 1 from 2 to 3. But they are all at right angles to each other. So I'm not going to rotate the axes with respect to each other. I'm going to rotate the whole configuration like it's like a left-hand rule or a right-hand rule in that regard, and I move the entire thing. And this is a mathematically complex situation that you find yourself. Like I said earlier, last class, students, and also from my experience when I was a student, I was taking these classes, it was probably the most complicated mathematically concept to grasp from geomechanics. And I'm really sorry it comes very early in the class, but I mean, that's how things are. Yeah, like I said, it's going to become harder before it gets better, but it will get better. Okay, so we need let me just make sure I'm sharing the right, sharing the right screen, and I am recording. We will use a matrix itself to move from the principal stress directions to the geographical and arbitrary geographical coordinate system. We call this matrix RPG. But I know it sounds like the bazooka, but it's like you're going is the matrix that will help you go from P to G, okay? And you will use something similar, a different version of that matrix we are gonna see later to go from G to P, okay? So that RPG matrix, it's very, very important, and it can have many forms. And we are gonna see the version that we use mostly in geomechanics is the northeast down version. And it's indicated by the right-hand rule. You have one finger pointing to the north. You have, say, the thumb is pointing to the north. The index is pointing to the east. And then the middle finger, sorry about that, is pointing down. And this is a little bit of the opposite of what aviation people are using. They use a northeast up, I believe, or something similar system. For us, because the wells are going down there in the subsurface, I think you understand that you need to use the northeast down system. And imagine with the right-hand rule. Now, imagine another right hand like this underneath your right hand. And then you move the top of them a little bit. You create three angles. The index finger has an angle from where it was the right hand initially, before you rotated it. That will be what we see here as angle it would be angle beta. And this is a very, very difficult to draw schematic. And this is the best I could find, honestly. And I tried to draw it myself. Honestly, it's really, really hard. But anyway, you have three angles. You have an angle from north, which is alpha, an angle from down, which is gamma, an angle from east, which is beta. But you have to understand that, just like the right-hand rule, take your hand, move it. You are moving the whole thing. You are not moving the fingers with respect to each other. they still stay at 90 degrees from each other. So you move it a little bit, you are creating an angle between two of the fingers, maybe, and then at least two of the fingers, and the the original placement. So in the original placement, you have alpha equals 0, beta equals 0, gamma equals 0. You move it, the system, the entire coordinate system, you create angles, non-zero angles. Joseph, do you have any question? No.
No.
Oh, okay. Okay. And now, let me, the RPG matrix depends on the projections of the elements of the new base to the old base. The old base is the fixed one, okay? Where it was originally, where alpha equals 0, beta equals 0, gamma equals 0. Then you shifted your system a little bit, you created non-zero angles, and you have to use these angles to create your RPG, which you will use in this manner to go from S, which is the geographical system, to principal system SP, or SP to go to S. Now, if you do go, you have two equations down here. Let me just make things easier by writing down. Okay. We talk here about G, which is the geographical system. This would be S. And we talk about P, which is the principal axis, and this would be SP, okay? You can either go from SP to S or from S to SP. You are either gonna use this equation to go from S to SP, or you're gonna use this equation to go from SP to S. And okay, we have the RPG in the equation, and it's like three matrices, and you have to go like, in the first equation has SP equals RPG times S times the transpose of RPG, which is basically flipping RPG. Row 1, column 1 becomes, well, I guess row 1, column 1, but say, it's like putting a mirror diagonally and flipping it. So this is row 1, column 3. It will become row 3, column 1. It will switch with this. So if I want to transpose RPG, I will do this. I will take, let's just see, I will take this, will swap with this. This will swap with this. And unless I'm very much mistaken, this will swap with this. Imagine putting the diagonal stays the same, and then you swap. It's like putting a mirror in the middle, basically. But mathematically, it's very easy. Row I, column J becomes row J, column I, and so on and so forth. And it's a complicated matrix. In fact, it has a name, RPG. What we call RPG here is what is known as the Euler's matrix. And you may have seen that before in your multivariate calculus class, or if you took a class on linear algebra for rotation of parameters. It was a very common mathematical exercise, but it can be simplified to something less complicated. I know it looks scary, a lot of symbols, a lot of angles, a lot of Greek letters. I like Greek letters, but it's a little bit too much. Yeah. Yeah, we will see what we can do to simplify it a little bit. But I want you to know that this is the main version of the RPG. Like if you have angle alpha, beta, and gamma, as we are going to see in the upcoming example problems, we just plug them in and get a simpler version of RPG, which you can use using the equations below to get the answer that you want. Now, like I said before, things will get easier. And it's not because of me, it's not because I want to, because of this guy called Anderson, E.M. Anderson, I forgot what it was his first name. He was British, I believe. And he was more on the applied side. So what we have said so far has more to do with the mathematical side of things, okay? That's why there is always a big question mark. Is what we are calculating making physical sense, or is it just numbers? And we are trying to make them follow a certain mathematical pattern. And Anderson was more on the geology side of things and said, excuse me, 1 second. I have been looking at different stress states in the subsurface, and what I have been finding is that, generally speaking, more or less, one of the stresses that we are looking for is vertical, and almost exactly vertical. And if you read in Zopac, in the textbook of the class, which you should be reading, even though I know it's a little bit not intimidating, it's a little bit, it starts from a pretty high level, but it's very, very applied focus. So it's like very, very focused on application, which makes it easy to follow. Whereas if you're an undergrad, if you're a graduate student, you may want to get into, at some point, you start from Zobac, but then you want to get into more theoretical. You start from application and the basics, and then you go to the fundamentals. That's the right way of learning, actually. Some people try to do the opposite, and it becomes a mess. Anyway, so this guy said, why don't we make our lives easier and say one of the stresses is always vertical? And I know that Zobac in the book says there are some significant exceptions to that. Like if you are near a salt dome, the stress state tries to also follow the stress dome, the shape, the stress dome, the salt dome, sorry. If you are near a salt dome. But in general, let's just make the assumption that one of the 3 principal stresses will be vertical or very close to that. And let's call that SV, since it's vertical. S vertical. The vertical in situ principal stress. That means that you have 2 horizontal. And those horizontal stresses, the other 2 in situ principal stresses, will be, one of them will be more compressive than the other. So let's call the one that is more compressive than the other S capital H max, the maximum horizontal in situ principal stress. And the other that is left would be the S lowercase h mean, which is the least compressive horizontal in situ principal stress. So now we have 3 stresses that are basically the vertical one and the 2 horizontal. And the only rule that we have is that one of the most compressive of the 2 horizontal will be called SH max, uppercase H, and the other one will be called S lowercase mean, SH mean, lowercase h. And that automatically, if we believe that this is true in the setting that we are evaluating, we are automatically simplifying mathematically the problem we are dealing with. Because I'm automatically telling you that one of the stresses is vertical, and then I have two horizontal, and one of them is bigger than the other, and I know how to call them, and I know their direction. If you tell me that SV is 1,000 in this place, I know where SV is located at, and I know I know the direction SV is pointing, and now I know the magnitude as well. And if you tell me the two horizontal are 8,000 and 6,000, automatically I tell you, oh yeah, SH max is 8,000 and SH mean is 6,000. Like you simplify the problem and makes, yeah, mathematically a lot more intuitive sense now. Yeah. Now, the only rule that we mention other than their direction, one is to be vertical and the two horizontal, is that SH max is bigger or equal to SH min. In the case that they are equal, we have what we call horizontal isotropy, and it doesn't matter what you call each because they are both either, you know, they are all the same magnitude. But the only real rule is that you cannot have SH min bigger than, more compressive than SH max, of course, and the directions that they need to be oriented at. Thanks to Mr. Anderson. So now, how many permutations do I have of a possible stress state considering Anderson's theory? How many? Joseph, you know the answer? Okay. 3. The answer is 3. I have 3 possible permutations. The first one is SV bigger than SH max, which is bigger than SH min, and we will call that the normal faulting stress state. That's something that you learn in geology, where the biggest of the 3 stresses is the biggest is the vertical SV, and then you have the smaller being the horizontal SH mean, and the intermediate being SH max. And now, so I know I wrote in probably behind my camera, so SH max is the red, and then SV is the blue. And I have obviously a arrow up there. Good point now is that, okay, this is a very common, in fact, it's the most common stress state that you can encounter in the Earth's subsurface. Classic example of that is the Gulf of Mexico. And we are going to talk later in this module why it is the case in a depositional deltaic environment. Geologically, I can end up with this kind of normal faulting stress state. That's the first one, first permutation. What about the second permutation? That's when SH max is bigger than SH min, and SV is the smallest of all 3. As you understand now, there is no rule of the magnitude of SV relative to the other 2. There is only a rule for the magnitude of SH max in relation to SH min. But in this case, SH max bigger than SH min, which is bigger than SV, we have what we call reverse faulting or thrust faulting. This is where what you encounter in areas where there is mountains, like the Himalayas, where mountains are created. And if you remember what we mentioned at the beginning of this module, that areas of high confinement when you hear horizontal confinement or even just confinement, think about the horizontal stresses, SH max and SH min. Okay, you have high horizontal stresses and you have a low vertical stress. So it allows the earth to move upwards, make a mountain by pushing it from the side. And in that case, let me draw the stresses. The strongest one would be SH max. The weakest one would be SV, and the intermediate one would be SH max. If you remember from geology, we have the foot wall and the hanging wall here on the diagrams on the left, on the right. If you forget what is the foot wall and what is the hanging wall, ask yourself which one looks like a shoe. And the answer is the one that looks like a shoe is this one here, foot wall, and then this one here, foot wall, and the other one is the hanging wall, hanging wall. No. Let me try to write it better. It's the hanging wall. Okay. And here it's the hanging wall. Some of them write them as one word, some of them write them as two words. But basically, you have the hanging wall and the foot wall. Imagine the foot wall staying stationary and the hanging wall moving. In the case of normal faulting, hanging wall is moving down because the confining horizontal stresses, i.e. SH max and SH min, are weak compared to the vertical. So the vertical makes it move down. In the other way, vertical makes it is very, very weak compared to the horizontal. So it makes the hanging wall move up. And it's like a mountain being created. If you have a piece of wood and you cut it off, I have at home somewhere, I don't know where I put it, you will imagine you can make a foot wall and a hanging wall and do this exercise. And then always the intermediate stress, SH max in the first case and SH min in the second case, is on the side that doesn't cause any motion, doesn't feel any motion. Now, okay, we have two of those permutations. What about the third one? The third one is known as the strike-slip faulting, which is, let me erase. Now, strike-slip faulting is a little bit weird. You have SH max being the stronger, SV the intermediate, and SH min the least. And so everything, the motion is completely horizontal. There is no vertical component in this motion, okay? So it doesn't matter what you call the foot wall and the hanging wall, both of them are the same. And what we have is the strongest one being in this direction, SH max, the most compressive. And then we have the intermediate one being the vertical, SV, and then the minimum one being least compressive one being SH min. Now, okay, this is a little bit weird compared to the other two due to the fact that there is purely horizontal motion. Well, in the other two, there was only vertical motion, no horizontal component. In this one, there is only horizontal component, no vertical component. A good example of that is the San Andreas Fault in California. Very easy to remember that, has the same name as your instructor, same first name as your instructor. Okay, now, we said it doesn't matter which one is the foot wall and the hanging wall in this case, but there is another aspect to it, okay? Imagine if I'm standing here. Imagine if I'm standing here. Okay, and I'm looking at the other way. Where do I see the other plate moving? It's moving to my left. Okay, now imagine if I'm standing here. Where do I see the other plate moving? It's moving again to my left. So this kind that we see in the schematic is a left lateral strike slip fault, also known as sinistral strike slip fault. It has to do with the ancient Greek word for left, which is sinistra. It's not the modern word. The modern word is aristera. But sinistral, sinistral, Simistral. It's a strike slip, left lateral strike slip fault, as we also call it. The opposite is possible. It would be called dextral if everything is moving to the right. That has origins to the modern day word for right, which is dexia. Dexia, dextral, means I'm standing and I'm looking at the other plate moving to my right. This is how San Andreas is actually. And if you remember, a comment made by one of the students in the first classes is that strike slip faults are very, very, it's the ones that are prone to very, very strong and long earthquakes. They can move long and they can cause a lot of damage. And that's the ones everybody's afraid of. Of course, you know a lot of stuff about San Andreas fall. Everybody's waiting for a big one there. There were cases where people were selling their homes. They thought it was a good opportunity. I used to have a professor that he went to Stanford and sold his home in San Francisco because he was afraid of the earthquake, even though he wasn't living no more, and he lost a lot of money. He tried to play the probability, where I think he was a geostatistics professor, if I'm not mistaken. I had a couple who went to Stanford, so more than a couple, so I don't know which one was. But yeah, visualization by relative movement of faults. By the way, I should have turned on the lights. That's what happens when there is no audience. It's like you don't know if. Also, you don't know if you made a mistake in the slides. Sometimes audience will point that out. This time there is no audience today. There is not much in classroom to point out. What else? We have foot wall and hanging wall. Let me just write now so that you avoid confusion. I will put F. What do I do? F, H. Okay, foot wall, hanging wall, foot wall, hanging wall. And now it doesn't matter, foot wall or hanging wall, foot wall or hanging wall. Yeah. So Mr. Anderson made our life effectively way easier by simplifying the stress state and also constraining the possible permutations with just three. But we are not completely done with rotation matrices and this kind of stuff. There is a little bit more to go about that. And you might have that in the future as well. I mean, especially people who are doing research in these matters, structural geologists in particular, and our department is led by a very, very good former structural geologist, is that it can get pretty mathematical, as you will see or have seen or can imagine. Now, before we go back to more complex, we are going to go even simple now. Okay, we talked about three stresses, right? Three in situ principal stresses comprising the stress field. SV, SH max, SH min. Okay, naturally, oh, by the way, good point, is that if we go back, remember what we said is that at the third lecture, we said something. We said that S1 is always more compressive than S2, which is more compressive than S3. Then we went a little bit more complex, and then we came back to those three again, but now we call them SV, SH max, SH min. Is it possible to relate S1, S2, S3 with SV, H max, and H min? And the answer is yes. Because for normal faulting, S1 is SV, S2 is SH max, S3 is SH min. For strike slip faulting, similarly, S1 is now SH max, S2 is SH min, S3 is SV. And for strike slip faulting, S1 is again SH max, S2 now is SV, and S3 is SH min. Okay, SV can be either more S1, S2, or S3. SH max can only be S1 or S2, and SH min can never be S1, so it can be only S2 and S3. So that's the relationship between the terminology that we have used already in this class, which I understand is already a lot and can be confusing. So you better stay on top of it. It can be very confusing if you leave everything before the exam. Now, okay, somebody said, okay, we have now three stresses, whether we call them SV, SH max, and SH min, or S1, S2, S3, we have three in situ principal stresses. Can I define the stress field in a particular location in the subsurface with just one value? How about I do that with just one value? One number characterizing the stress field in a particular subsurface location, only one value. And this person was Mr. Simpson in 1997, not OJ. He developed a term, he called it alpha phi, which varied from 0 to 3, and is used to describe a stress state, basically the combination between SV, SH max, and SH min. And it was a correlation he came up with, which is given by this. And it's a little bit complex, but it should lead to a value in the range from 0 to 3. And how does that work? If you are in a normal faulting stress state, SV is bigger than SH max, which is bigger than SH min, and your N should be 0. So if you're in a normal faulting stress state, you will use 0 here. Your S1 will be SV, your S2 will be SH max, and your S3 will be SH mean. And the answer that you are gonna get for alpha phi is that it can vary from 0 to 1. Okay, what happens when alpha phi is 0 means that your SV is way bigger than SH max, which is very close, I guess, almost the same as SH mean, or compared to SH mean. What is alpha phi equals 1? Alpha phi equals 1 is SV is equal to SH max, which is bigger than SH mean. So you are in the interface between strike slip and normal faulting with strike slip at alpha phi equals 1. Now, if you have a strike slip stress state where SH max is bigger, SV is the S2, the intermediate, and H mean is S3, you get a different situation where you have to use n equals 1 here and here. SV equals is the S2, SH max is S1, SH mean is S3. And now you go from alpha phi equals 1, which we said is the interface between normal faulting and strike slip faulting, to alpha phi equals 2, which is SH max is how is that? Is it SH max is bigger than SV, which is equal to SH mean, I believe. Okay, and if you have a strike slip faulting stress state, now what do you have now? You have reverse faulting or thrust faulting. SH max is S1, SV is S3, SH mean is the intermediate, S2, and you are forced to use n equals 2. So minus 1 to the power of 2 becomes 1, right? What is in the parenthesis? S1 is SH max, SV is S3, SH mean is the intermediate, and now you are going to be ranging from alpha phi equals 2, where what we said there, SH max is bigger than SV, which is roughly equal but bigger than SH mean, to alpha phi equals 3, which is the highest possible alpha phi value, where SH max will be way bigger than SV, which is bigger than SH mean. Let's see, something is, I think it's correct the way I did it, but don't worry so much about the stuff on the left side that I wrote here. Worry about just the ranges. Like, don't expect a normal faulting stress state to have an alpha phi of 3 or a 2.5 or something. It would be a reverse. always ask yourself if the answer makes sense. Remember, is what we said. And then there was another excellent structural geologist, one of Zopak's graduate students. Actually, the guy is my age, I believe. Dr. Lundstern. He got married recently and changed his last name. He went to Stanford. He said, let me take this alpha phi scale from 0 to 3 and paint maps in accordance to that scale. And the result was excellent, actually. He did a great job. Took him a long time. He looked into several places. This is one example. Look at how beautiful this map is colored to indicate the stress state. Dark blue is like alpha phi equals 0. And dark red is the alpha phi equals 3. And in between, you have all the colors of the spectrum. And you see where we are in between North Dakota on the extreme east end of North Dakota, near Minnesota, where I put a dot. It's like a greenish color, tending to become blue as in the south, as we move in the south west of where we are. Is basically somewhere near alpha phi equals 1, which means we are in the strike slip normal faulting interface, more or less. It's strike slip becoming normal and vice versa. This is because, as we know, the backend, so I give you values for the backend, typical values for the backend shale. SV is 10,605 psi. SH max is 10,302 psi. SH mean is 8,080 psi. That means my SV is roughly equal to SH max. And they are both bigger, much bigger than SH mean. So we're roughly at alpha phi, roughly equals to 1-ish. I calculated it once, I don't remember exactly the value, but of course it varies. But this is an excellent way. I believe he works in USGS and he's located in Lakewood, Colorado. Jean-Eric Lundsny is his old name. Now his last name is Lundstern. He has a beautiful website, and you can go in and put your values of SV, SH max, SH mean, and it can tell you the value of alpha phi. But this is not really for you guys because you know how to calculate it now. So, but yeah, beautiful maps. Very easy way of like color coding everything. And I give you his website. I'm sure he doesn't mind the traffic. Yeah, here. jenslundstern.com stress hashtag alpha AFE calculators. But I mean, you should be able to write a code or an Excel spreadsheet yourself that would be able to do that. And I think that's a good way to stop the class. I think we learned enough for today. We have covered a lot of material. Make sure you digest it, go through it. The good thing with the recordings is that you can pause it whenever you want and think. I remember when I was reading books by my favorite authors, technical or non-technical, I always take time and read a little bit and then stop and think. And then read a little bit, stop and think. Sometimes when I was on the beach at home, I will walk a little bit and then come back and keep reading, good days. But anyway, yeah. Yeah. So we'll talk about it next time. Thank you very much. Have a nice rest of your evening. And we'll see you on Wednesday.